In this video, we are going to be learning about intermolecular forces, which are attractive forces between molecules. Intermolecular forces, which I will abbreviate IMFs, are attractive forces between particles. The prefix inter means between. It is these attractive forces between particles that influence many of the macroscopic physical properties of a substance. The stronger the intermolecular forces between particles, the higher the boiling point, the higher the melting point, the more viscous the substance will be, and the greater surface tension it will have. Our goal is to be able to look at the Lewis structure of a substance and predict what types of intermolecular forces are present within a pure sample of that substance. Here are some examples of how intermolecular forces play a role in everyday life. When you do laundry, water can disrupt the intermolecular forces between fibers in your clothing. As the clothing dries, it can become wrinkled if the fibers are no longer aligned in the way that you prefer. To remove these wrinkles, you have to apply heat and pressure to break and reform the intermolecular forces in a more orderly arrangement. You may have seen lizards climbing on walls. The pads of their feet allow them to maximize their contact with the surface. They adhere to the wall through dispersion forces, which are a type of intermolecular force. If you have ever tried to mix oil and water, you have probably noticed that they do not mix. The oil floats on the water because water is more strongly attracted to itself than the oil. Soap allows oil and water to mix because it contains both polar and nonpolar regions. Some fabrics are coated with waterproof coatings. These coatings prevent water from forming attractive intermolecular forces with the fabric, so the water is more strongly attracted to itself and beads up on the surface. Your DNA contains two strands held together with hydrogen bonds. Hydrogen bonds are an intermolecular force that are weaker than covalent bonds, which allows enzymes to unzip the DNA strands during replication or transcription, and then reform the hydrogen bonds afterwards. The attraction between two particles ultimately comes down to opposite charges. If you have a fully positive cation and a fully negative anion, the attractive force between them is so strong that we call it an ionic bond. Ionic bonds hold together ionic compounds. Polar molecules also have opposite charges, but they are only partial charges. Remember that the delta symbol represents a partial charge. An attractive force between one dipole and another dipole is called a dipole-dipole force. Sometimes chemists are very creative when naming things. Likewise, an attractive force between an ion and a dipole is called an ion-dipole force. And it can happen between either a positively charged cation or a negatively charged anion, just with opposite ends of the dipole. We will focus on three intermolecular forces: dispersion forces, which are the weakest, dipole-dipole forces, which are medium strength, and hydrogen bonding forces, which are the strongest of those three forces. All three of these intermolecular forces are much weaker than ionic or covalent bonds. Hydrogen bonding is the strongest of the three intermolecular forces we will study, but it is still significantly weaker than an ionic or covalent bond. It is roughly 1/9 as strong as a typical covalent bond. The first intermolecular force we will discuss is dispersion forces. All atoms and molecules experience dispersion forces. Electrons are constantly moving around the nucleus. At any instant, the electrons may be unevenly distributed, creating an instantaneous dipole. When the electrons shift towards one side, the opposite side becomes more positive. This can attract the electrons on a nearby atom, creating an induced dipole. These temporary dipoles create weak attractions between atoms and molecules. Because the electrons are constantly moving, these attractions are continuously forming and disappearing. Although dispersion forces are considered the weakest intermolecular force, many weak attractions can add up to become more significant. Think of a sheet of Velcro. One hook and loop connection is weak, but thousands of them can come together to create a very strong attachment. Larger molecules contain more electrons and have greater surface area, allowing them to experience stronger dispersion forces. We can use molar mass as a quick way to estimate the relative size of atoms and molecules. This table shows the boiling points of many hydrocarbons. Molecules made out of only carbon and hydrogen are nonpolar, so the only intermolecular force present is dispersion forces. The increase in boiling point shown in the table is due to the stronger dispersion forces in the larger molecules. Notice that all of these boiling points are negative. As the values become less negative and move closer to zero, the boiling point is increasing. Dipole-dipole forces are attractive forces between polar molecules. Polar molecules have permanent dipoles, meaning they always have one end that is partially positive and one end that is partially negative. Because these dipoles are permanent, dipole-dipole forces are stronger than dispersion forces. Opposite charges attract. In these hydrochloric acid molecules, the partially positive hydrogen atom on one molecule is attracted to the partially negative chlorine atom on a neighboring molecule. The dotted line represents a dipole-dipole attraction between these two molecules. Look at the Lewis structures for the three substances below to determine whether dipole-dipole forces are present in a pure sample of each substance. The first substance is carbon disulfide, CS2. The molecule is nonpolar because it is linear in geometry and is symmetrical. The bond moments cancel. This is a nonpolar substance. Nonpolar substances experience only dispersion forces. Our next substance is difluoromethane. This molecule is polar because the carbon-fluorine bonds are polar covalent, and the tetrahedral arrangement is asymmetrical. There is no way for two fluorine atoms to be directly opposite from one another in a tetrahedral geometry. They are always separated by a bond angle of approximately 109.5 degrees. Because this molecule is polar, it experiences dipole-dipole forces. Lastly, we have tetrafluoromethane, CF4. Although each carbon-fluorine bond is polar covalent, the molecule is perfectly symmetrical because all four terminal atoms are fluorine. The bond dipole moments cancel, making CF4 a nonpolar molecule. Nonpolar molecules experience only dispersion forces. The last intermolecular force we will discuss is hydrogen bonding. Hydrogen bonding is an especially strong dipole-dipole force that occurs when hydrogen is bonded to a small, highly electronegative atom. There are two requirements for hydrogen bonding. First, the molecule must contain a hydrogen atom that is covalently bonded to a nitrogen, oxygen, and fluorine. This hydrogen is called the hydrogen bond donor. Second, a nearby molecule must contain a lone pair of electrons on a nitrogen, oxygen, or fluorine. This molecule acts as the hydrogen bond acceptor. As long as one molecule can donate a hydrogen bond and the other molecule can accept it, a hydrogen bond can form between them. This drawing shows several water molecules. Water molecules can hydrogen bond to one another because each water molecule contains both hydrogen atoms bonded to oxygen and a lone pairs of electrons on oxygen atoms. Although hydrogen bonding is a strong intermolecular force, it is still much weaker than ionic or covalent bonds that hold compounds together. Hydrogen bonding is also found between the two strands of DNA. This close-up shows the nitrogen-containing bases that make up DNA. Cytosine and guanine can form 3 hydrogen bonds between one another. In this model, oxygen atoms are shown in red, hydrogen atoms are shown in white, and nitrogen atoms are shown in blue. Notice how the hydrogen atoms bonded to nitrogen are attracted to lone pairs on nearby oxygen atoms and nitrogen atoms on the complementary base. This slide summarizes the different forces of attraction. Dispersion forces occur between all atoms and molecules. However, nonpolar molecules experience only dispersion forces. Dipole-dipole forces occur between polar molecules, which means molecules must contain polar covalent bonds and have an asymmetrical shape. Hydrogen bonding requires both hydrogen bond donors and hydrogen bond acceptors. Ionic bonds and covalent bonds are actual chemical bonds, and they are much, much stronger than the 3 intermolecular forces that we have discussed. Ionic bonding occurs between oppositely charged ions in an ionic compound. Covalent bonds hold nonmetal atoms together within molecules. There are no covalent bonds between separate molecules. Here's a practice problem. Identify the strongest attractive force between particles of each of the following pure substances. Choose from ionic bonds, hydrogen bonding, dipole-dipole forces, or dispersion forces. The first substance is BH3. BH3 is nonpolar because the electronegativity difference between boron and hydrogen is only 0.1, making the boron-hydrogen bonds essentially nonpolar covalent. The molecule also has its symmetrical trigonal planar geometry. Therefore, the strongest attractive force is dispersion forces. Next is water. Water can form hydrogen bonds because it meets both requirements. Hydrogen is bonded to an oxygen, and oxygen has lone pairs. Therefore, the strongest intermolecular force is hydrogen bonding. Next, we have magnesium oxide, MgO. Magnesium is a metal and oxygen is a nonmetal, and the electronegativity difference is greater than 2. This is an ionic compound, so the strongest attractive force is ionic bonding. Our last substance is ethanal. This molecule is polar because it contains polar covalent bonds and it has an asymmetrical structure. However, it cannot hydrogen bond with itself because the hydrogen atoms are bonded to carbon, not to oxygen. Since it does not meet the requirements for hydrogen bonding, the strongest intermolecular force is dipole-dipole forces.